This article is related to physics-informed neural network for solving the one-dimensional heat equation in MATLAB. And basically, in physics-informed neural networks, I have just used the mesh-free computational framework for the solving of partial differential equations by embedding physical laws directly into neural network training as well. So the thing is that in the partial differential equations, we have to solve the partial differential equation using the physics-informed neural networks to find out the one-dimensional heat equation with the prescribed initial and the boundary conditions. So the fully connected deep learning neural network, which is basically trained by minimizing a composite loss function that enforces the heat that enforces the heat loss as well as the heat absorbed uh, in the basically specific material. So the automatic differentiation basically is employed to compute the spatial and temporal derivatives required to evaluate the physics residual. So the thing is that in our proposed methodology, which we have added the pins methodology, it is basically provide us the numerical solution and numerical experimental solution to convergence for the metals convergence and its stable and learning behavior. So I have just solved one-dimensional heat equation with the predicted temperature profiles. Shows the excellent with the corresponding analytical solutions as well. So our results basically provide us the accuracy and robustness of pins for the parabolic partial differential equation solution. So here is I have just written the abstract with the keywords and the introduction. So this is the basically first figure which is performing the physics-informed neural network-based heat equations on a specific metal. Okay, so the training process takes some time for the solving of partial differential equations. So instead of relying solely on label data, pins basically utilize the physical laws as soft constraints to guide the network learning as well. So see, this is basically the solution of heat equation using a neural network. So pins offer a mesh-free alternative capable of solving of partial differential equations on continuous domain without explicit spatial discretization. So this is a complete introduction with the background. Like in the background, we need to review like how the pins for the partial differential equation problems has been provided and how conventional methods are used, like the finite difference, finite element, and finite volume operators. These are the conventional methods, and it provides us basically that methods required discretization of both space and time domains as well. So like although these techniques provide accurate solutions, they involve mesh generation, handling of stability conditions, and often large computational costs for the fine grids. And complex geometries and multidimensional extensions further increase this burden as well. But in our method, which is basically physics-informed neural network, provide us the geometric adaptive convolution neural network for solving the parameterized steady state on the partial differential equations basically. So this approach basically offers a physically constrained training and mechanism that reduces the reliance on labeled data. Consequently, pins basically presents a promising alternative framework for the numerical heat transfer modeling. Okay, so here is a role of physics informed neural network. Basically, like role is same like how we can capable to provide capable for the thermal diffusion modeling, and how we provide as a suitable test bed for the evaluating of pin accuracy and reliability. So the problem and challenges, like as we have discussed, the previous methods are costly and it provides us a lot of burden on the um, in the calibration of different softwares. So it take a lot of time. So that's why we have used the pins method, which provide us a uh, relatively low time for the calibration and simulation purposes. So here is the objective and contribution, like how we can implement in the MATLAB with its accessibility for the engineering research, and how we provide us the performance metrics such as mean squared error and the absolute deviation, all used for the quantitative evaluation. Okay, so with the problem statement is written here: mathematical approach, mathematical modeling. These are the equations used for the partial differential equations, and the sine wave function, which is basically a range from 0 to 1. 0 to t means 1. So representing of single mode spatial excitation. These are the equations used for the exponential with the multiplication of sine pi x basically. So these are the residual defined as well, and the methodology as well. This is a methodology in which I have added the one-dimensional heat equation with the MATLAB almost 6,000 training approaches. So due to 6,000 training approaches, it takes some time and during the running of the MATLAB, but we will handle this accordingly and design MATLAB simulation and analysis. In the MATLAB simulation analysis, I have added all the layers, activation function with the training algorithm, learning rate, number of approaches, and evaluation grid as well. Okay, so the neural network is basically fully connected with the feed-forward network with the hidden of 50 neurons. Okay, so here is the training loss, which is basically 6,000 approaches accordingly, and here is basically the overall confirmation of the pin predicted. So this is a 3D surface plot for the exact analytical solutions as well. And next one is basically absolute error, 3D surface plot for the absolute error across the domain. Here is basically heat map provides a top-down view of the error distribution across a spatial temporal domain as well. Here is the comparison of pins predictions and the exact solution selected from different time scales. Okay, here's a result and discussion like how we provide us the confirming of the high accuracy of the model, and how the time slice comparison further validate the predictions, showing the excellent agreement between the pin's output and the exact solution at multiple time instances. So yes, it is almost PDE and everything is completed. So let me just then conclusion and the references as well. Let me just open the MATLAB code. Actually, I have just run the MATLAB code because it takes some time, a lot of time. Pins heat.1d.m. So these are the MATLAB code in which it provides us the training dataset with the initial conditions, boundary dataset, normalizations as well, network of all layers. So it takes some time. So that's why I have just run this MATLAB code in previously during the uh, explanation of articles, so that it will provide us the accurate results You just need to open this MATLAB file and just run it. It will take some time because the patches are 6,000, so one by one it just run it accordingly. So these are the MATLAB results generated by the training loss, predicted pins predicted, exact solution 3D surface, absolute error, heat map error, and the output results for the pins prediction as well. Okay. So if you need to ask anything, you just ask me, I will answer your questions. Thank you.